Starting. All attendees are in listen-only mode.
Good afternoon and welcome to Deep Learning Clojure with Jonathan Graham. Before I hand over, just a brief note on eSynergy Solutions. eSynergy specialise in open source and cloud resourcing. If you're looking for a new opportunity or to build out your team, please get in touch after the webinar. Now, moving on to some housekeeping. If you have any questions for Jonathan, please fire them over via the question box throughout, and Jonathan will answer them at the end of his talk. We are recording the session, and the slides and recordings will be made available and sent to you tomorrow along with my contact details. Now I'm going to pass you over to Jonathan to begin his talk.
Share my screen. Hopefully you can all see my screen. So I think it's afternoon with you, with most of you there. It's actually morning with me. And over the next hour or so, we're going to be taking a bit of a deep dive into Clojure, having a look at some of the guts of the language so that we can understand what it is that we are doing as we're writing our code. So I mentioned it was morning here. I am actually at the moment in Waynesburg in Pennsylvania. So if you can see, it's over on the east coast of the States. We're about 4 or 5 hours drive west of New York and Philadelphia. And I'm actually there, moved there because of Mind Minds, which is an organization that I've co-founded, and we teach unemployed and underemployed people how to program. And we also employ people as a consultancy afterwards. And one of the key things that we do is focus on the fundamentals. We really have the mantra of learning the fundamentals because everything else changes anyway. And that was a quote I heard a few months back from Dean Wampler, and it's something that really resonated with me. If you understand the building blocks and how it all comes together, then as everything changes, you can make sense of it and you can adapt as the industry changes. So what we're going to be doing over this next hour is looking at some of those fundamentals of Clojure. So I'm not sure how many of you are completely new to Clojure, or whether you have some experience. But regardless, if you go into any new language, you always have a choice of how you go about learning. So just for a moment, I think with the last language that you took, or if you're starting a new language now, how are you approaching learning that language? And in Clojure, we're lucky. There's a lot of resources for us. I actually started with a project with overtones, so making music, and that was my introduction into Clojure. So having some sort of a hobby or side project that gets you into the language is a great way to learn. And then beyond that, there's resources that give us exercises to get into the syntax and the functionality of the language, so things like the Clojure koans and foreclosure. So they're great for giving you hands-on experience, getting going with the language, writing the first code that you do. Of course, there's plenty of books out there. It's an example from Karen Meyer, Living Clojure. And there's webinars, meetups, blogs, etc. that give us some of the resources that we need in order to start immersing ourselves in a language and getting ourselves up to speed on how it works. So I've taken these approaches before, and yet it's something different that I'm going to be talking about today, which was really helped me with Clojure and that I'm using with other languages to really get into the guts of understanding how a language works. And that is to implement models as some of the core functions. So in effect, we're going to write the language in that language in order to really learn how the language works and functions. And so it's kind of like if we're playing with Lego and building a house, we're not going to actually build a proper livable house, but we're going to get an idea of how things can be structured, what sort of a layout we may want, what sort of functionality we need, and how things all work together. So what we're going to do today is just look at a few of the core core functions in the Clojure language, and we're going to write our own models of them. So what we're not trying to do is have an exact mimic of what's out there already. We're not completely rewriting the language. We're just writing models of some of those functions so that we can understand how the language really works, what makes it powerful, how it can all come together. So, and for the purpose of today, we're not going to look at things like the efficiency of the functions we're writing. That's going to be outside of scope. We're going to be looking at, given certain inputs, how do the functions work so that we get the desired output? The first thing that we're going to start with is kind of symbolized here. So if you can see from the diagrams maybe what we're going to start with. And it's going to be reduce. So we're going to start by looking at reduce. And that's really because that's one of the backbones to the Clojure sequence functions. So that's kind of what these diagrams are here. So reduce being the backbone of the Clojure sequence functions. So it's a great place to start. One of the things I struggled with this slide was what's a good representation of sequence? Because sequence can mean a lot of things. So what does it mean in this context of sequence functions? So pull out a dictionary definition. I think this was Merriam-Webster. And it lets us know what a sequence is. So a particular order in which related events, etc., follow each other, or a set of related events that happen in a particular order, or we can arrange things in a particular order. There's different definitions for what sequence can mean, but does that actually help us when we're looking at what are sequence functions in Clojure? What helped me, there's a blog post by Alex Miller and talking about sequences, and it explains here that the sequences is the key abstraction that connects immutable persistent collections with the sequence library. So we can break that down a little bit. Clojure manages state through having immutable collections, so vectors, lists, sets, etc., being immutable and persistent. So rather than changing values, we create new ones, and they're persistent. So even when we've updated the collections we have, what we had before remains persistent. So that's the immutable persistent collections, and they're related to the sequence library. So sequence library gives us the sequence abstraction functions. And so there's a few key ones. We're just going to talk about 3 here, and then we'll introduce another couple as we move forward. And these help us think about how we can work with collections, and so how these sequences actually work. So the first one is first. So if we apply first to a collection, it's going to return the first item of that collection. So in the example here, if we have a vector with 3 integers in, 1, 2, 3, and we apply first to it, we're going to return the first item. It's fairly self-explanatory. We return 1. We then have rest. And so applying rest to a collection, it's going to return everything but that first item. So in the example here, if we apply rest again to the vector 1, 2, 3, we're going to return a sequence containing the items 2 and 3. If we apply rest to an empty collection, then we return an empty sequence. And the final one we're going to use at the moment is cons. So this will construct a new sequence with the item prepended to the collection. So cons, applying cons to an item in a collection. And so in the example here, if we do cons for and the vector 1, 2, 3 again, we're going to end up with a sequence where we have 4 at the front and then 1, 2, 3 following. And so we can use these sequence abstraction functions in order to work with our sequence functions. So now we've got an idea about what sequences are in Clojure. we're going to have a look at what reduce is. So this comes from Clojure core, and there's obviously a lot here about what reduce does. So we can see on the first line, reduce is going to take either 2 or 3 arguments. It'll take a function, an optional value, and a collection. So the function it takes should be a function of 2 arguments, so val and the col. And we're going to, because there's a lot here, we're going to break it down. We'll first look at the situation where val is supplied. So where we're reducing the function, an initial val, and a collection. So if that initial val is supplied, we're going to return the result of applying the function to that val and the first item in the collection. We'll then apply to that result the function again and the second item. And we'll carry on through until we've iterated through the collection. If the collection contains no items, we're just going to return val and the function is not going to be called. So to really understand what this means, how this works, we'll start writing reduce and so that it works for this part of the requirements. And we're going to build this up in a TDD fashion. So we'll start with a test. For those of you that are new to Clojure, just a little bit about some of the syntax and the setup. So we start on the top line. We've got our namespace where our code is kept. So we've got a project, Clojure functions, and in this namespace we're looking at the spec for reduce, so our reduce spec. And we can require in libraries. So I like the speckle testing framework, so we're requiring that in. And we're also going to be requiring in the namespace where we're actually writing our reduce function. The refer all is just that we're going to be able to access all of the different functions within that namespace. So, good first test. We can look at what happens if we apply a function just to a value and an empty collection. And as a concrete example, we can use addition. So we're going to add an initial value of 1 to an empty collection. And so that should return 1. So we saw this really in the definition. So in our namespace for reduce, we can define our own reduce function. So we're going to define my reduce as a function that takes 3 arguments. So it takes the function. So for this first test is going to be addition, takes an initial val. So in this first test is going to be 1, and a collection. And we've got an empty list here. And what we wanted was, in the case with an empty collection, we just return val without the function being applied. So we can get this first test to work just by returning val. And that's test 1 done. So what about just moving on, the next obvious thing, what happens if we have a single item in the collection? So we can have a list with just a single item, 1 again in it. And so what reduce should give us is the product of applying the function to val and the first item in the collection. So we're adding 1 and 1, which gives us 2. So we can write this up to get both of the tests to work. And we can do this, we can, just in English to start, we can just say if we have an empty collection, so if the collection is empty, we're just going to return the initial val. So this means this will still work for the first test where we had an empty collection, it's just going to return the initial val. If not, so if the collection isn't empty, we can apply the function to the initial val of 1 and the first item of the collection, which is also 1. So we're just doing plus 1, 1. In Clojure we have the operator first, followed by the arguments. So plus 1, 1 is 2, and so that will make the second test work. So this works, but it's not quite idiomatic Clojure. We can just look at another couple of the sequence abstraction functions. So sequence and seek. If we apply sequence to a collection, we're going to return a sequence. So we're going to convert that collection into a sequence. If we apply seek to call, it's very much the same, except in the case where we have an empty collection. So in the case of sequence, we return an empty sequence. In the case of seek, we return nil. And so we can use this in order to change our condition where we're looking whether the collection was empty or not to use idiomatic closure. So we can say if seek call, so if seek call is truthy, so if there is a collection returns, it's going to be truthy, in which case we're going to apply the function addition to val1 and the first item in that collection, which in this case was 1. So we've got an item in the collection, we're going to apply the function to val and the first of the collection. If we've got an empty collection, like in our first test case, this will return nil, which is falsy, so then we just go down the other branch and we just return val, so 1. So now we've got this running in more idiomatic closure. So that works with just the one item in the collection. What about when we have more than one item? So another test, this time we've got a collection with 2 items in, 2 and 3. So as we iterate through applying addition, so 1 plus 2 is 3, and then we apply addition again to that result in the next item in the collection, 3 plus 3 is 6. So we've got a test where we expect to get 6 back when we apply addition to 1 and a vector containing the items 2 and 3. So in order to get this to pass, we can write the function recursively. So if there are items in the collection, so if seek call is truthy, we want to apply the function to the val and the first item in the collection, as we were doing before, and then we want to pass this back to our myReduce function with the function again and the rest of the collection. So we're going to set val, as we recurse through, we're going to set val to be the result of applying f to val in the first of the collection. And we'll carry on iterating through until that collection is empty, at which point we then just return val, so that reduced value that we've got. So this works, and we can add tests for different functions, collections, initial values, etc. And they can work. But there is an issue here. So if this is just a screenshot from the REPL, so pulling that function into the REPL, and we can look at larger collections. So in this example, we're applying myReduce, again addition, initial value 0, and we're applying that to the collection, which is the range 1000. So this is going to be a collection of all the integers from 0 through to 999. And we can run this. This works. It gives us the answer, 499,500. Okay, all good. What about if we just increase that collection? So now we're doing the range 1000. So a collection with all of the integers from 0 up to 9,999. We do this. It should work, but we get a Stack Overflow error. And why do we do this? It's because recursion consumes stack space. And so we run out of space as we iterate through, as we recurse through. So Clojure gives us the ability to use a special operator, recur, which gives us tail call optimization. So with this, we can get constant space recursive looping by rebinding and jumping to the nearest enclosing loop or function frame, and in this way giving us the tail call optimization. So if you can see, again, this screenshot from the REPL, instead of now on the third line down, instead of just calling the function name, we can use this special operator recur, and that's going to help us with the looping for the tail call optimization and mean that we are not consuming the stack space. So now, how many zeros have we got? 10 million or so items in the collection, and it deals with doing the reduction fine, so we get the answer out. So recur, when we're doing recursion in Clojure, we need to remember to use this special operator so as to avoid the stack overflow. So that's the situation where we did get initial val. What if that initial val is not supplied? In this case, we need to just apply the function to the first two items in the collection and set this to val, and then we can continue as we did before, applying function to that result val and the next item in the collection. So in order to do this, we can build a new arity for myReduce. So in Clojure, we're able to have different arities which contain the different arguments coming through. So we can have the case where we just have two arguments, the function and the collection. And we can have a test for this. So if we're passing addition again and a collection with just a single item 1 in it, we should just return 1. So how do we write this? We got the new arity, so on the top, and all we need to do is take out the first item of the collection and set that to val, and then the rest of the collection can be the collection. So we're going to pull out from the collection the first item and the rest, and then we can pass that through to our arity, which takes the 3 arguments. And so we'll have pulled out for this test 1 has been val, and the rest of the collection is empty. And we've already talked about that situation. We know that that works, and so our test passes. And we can simply add more tests with multiple items in the collection, and this code still holds true. So what happens still having no initial val and our collection contains no items? So we've just got an empty collection. In this case, we need our function to also be able to accept no arguments, and reduce is just going to return the result of calling that function with no arguments. So we can write some tests for this. So at the top, if we have addition again, no val and an empty collection, we're just going to evaluate addition, and the identity of that is 0, so we should get 0 back. And we can do the same for multiplication. This time we should return 1. In order to get that test to pass, we just in the arity where we've got the 2 arguments, the function in the collection, we just need to add the same ideas we had before, where if we've got items in the collection, so if seek call is truthy, we'll continue down the path that we had before, where we call myReduce, where the first item in the collection is now val, and the rest of the collection is the new collection. If the collection is empty, we simply want to evaluate the function. So within parentheses f. And this works. Those tests pass. And so we've done what was required from reduce. We've got a model of reduce that works whether we have an initial val or not, and for the case when we have empty collections. One of the things it showed us is that we really need to take care with functions that cannot be evaluated without any arguments. So we looked just before, we had tests for addition and multiplication. What about if you're trying to use minus for this? So we're going to reduce with minus and an empty collection. That then means we need to evaluate the function minus on its own, and this doesn't work. There isn't a result for that. So in these cases, we need to be careful. We either need to ensure that we don't get a situation where we can pass to reduce with that function with an empty collection and no initial value, because we know that will break. Alternatively, we've now seen how we can just write our own reduce function, so we can modify it as we want, so it can define differently what to do when we pass a function with just an empty collection. So we could modify it so instead of just evaluating the function, for example, we can send back an error code or whatever else. We've also seen that reduce allows us to work with functions that require 2 arguments, but only pass into reduce a single argument. So as an example, we can just write an addition function, so defining add with 2 arguments, x and y, and that will return just the addition of x and y. So if we try to evaluate just add and a single item, so add 1, this will obviously error, but we can pass to reduce add and a single item as long as it's a collection, and this will still work. So reduce add with a vector with 1 item in, 1, will return 1 for us. So it opens up some possibilities that if we haven't deeply thought about how reduce works, we may not have realized. So that was reduce, and that's, like I said, a backbone to many of the sequence functions. And so we'll see that now with count. It's a nice example to use what we've already learned from reduce. So count, we're just going to return the number of items in a collection. No return 0. So it's nice and straightforward what the requirements are. We can build this up in a TDD fashion again. I'll actually put the first few tests in here. So if we're passing an empty collection or passing nil to our count function, then we should return 0. If we have a single item in the collection, so the third test down here, then we should return 1. We've just got 1 item, so we've got a count of 1. So we can just quickly set up the function to make those pass. So defining our myCount function, it's just going to take the 1 argument here, the collection, and if that collection contains items, then we're going to return 1. So that at least gets the third test passed. And if not, if the collection is empty, then we just return 0. Nil is also falsy, so that will return 0. So just this simply sets up the function to make those first few tests pass. And then we can look at how to extend this when we have more than 1 element. And we can do this recursively, again using the recur special operator. So when we pass in the collection, we can set up a loop point where we can set within the extent of the loop that we can just recall call C. We could have just kept calling it call, and we're going to set result. So this is going to be our count result, and we want to initialize that as 0. So if we have an empty collection, so if seek C is falsy, then we're just going to return the result. So if we're going straight down that path, we return 0, 0 for a count for an empty collection. If there are items in the collection, then we're just going to recursively go back to the loop point. Now with the rest of the collection, so iterating through, and we're just going to increment the results. So every time we go through, we're going to increment the results until seek C returns nil, at which point we return the result. So this works. We can have tests for different collection types and different amounts of items in it. So we can build up a test suite and then look at this, and maybe we can refactor this. What are we doing within the loop? We're simply iterating through our collection, and every time we iterate through, we're just incrementing a result value. So we're taking a collection, we're iterating through, and reducing that to a single value, which in this case is the count. So that's basically what reduce does. So let's refactor this code using our reduce function that we'd already written. So what do we want for the initial file? We're going to have 0. We want to have a count of 0 as the initial file, so if we have an empty collection, we just return the file as 0. We're then going to pass in the collection. So my reduced, we've got the initial file in the collection. The function is going to be, we can just write an anonymous function where we set our results. So we're initializing that with 0. And we also take in the collection. But we don't care about the name of the collection because we're doing nothing with it. We're only iterating through. And every time we iterate through, we're just going to increment the result. So our function is going to increment a result, and we're initializing it with 0 in the collection. So in this way, we're using reduce, iterating through, reducing down to a single value, which is our count. And we've already got the test suite, it passes. So I found this a useful way of working with TDD, just building up logically, getting a function that works, getting a test suite that gives us confidence that the function is working, and then we can refactor that to cleaner code, more concise, and potentially more efficient. Okay, so we've got count. The third function we're going to talk about is filter. And you can see the first part of this, filter returns a lazy sequence of the items in a collection for which the predicate of an item returns true. So we're going to work our way through a collection, we're going to apply the predicate to each item in the collection. If that's true, we're going to add that into we're going to return a lazy sequence of those items. There is the case with filter where we can just pass it a predicate and no collection, and this would return a transducer. We're not actually going to cover that this morning. So we're just going to look at the case where we're passing the predicate and a collection to filter, and that should return a lazy sequence of the items for which the predicate returns true. So this opens up the question, what are lazy sequences? And so we can look how this is defined. You know, a lazy sequence created by the macro lazy-seq, and it goes on. We can just take some take-homes out from this. So lazy sequences can be infinite. Computation is performed as it's needed. So we're not going to go through the entire sequence, do the computation until we actually need it. That's the laziness. And so in this way, the full realization of the results can be avoided. So we're going to see what this really means initially by building up filter incorrectly. So we're going to have a look. If we don't build up filter lazily, what are the implications of that? So in that way we can see why laziness is important, and we can look at how to actually build that. It's the failing and what we learn from failing is a great way for learning. So if you end up at a situation and you're not quite sure how things should be working, just get something there and explore how it works. If it fails, that's fine. We'll learn things from it. So just got the code up for how we can build this recursively, so we can just step through it. It's quite similar to how we set things up for filter initially. So we're going to have a loop. We're going to have our input as the initial collection, so just within the loop we're setting call to input. And we're going to have our result, so our filtered result, and we're going to start that, initialize it with an empty vector. So we could have chosen different things here, but if you choose an empty vector, we can just treat things in the same way as we go through. Okay, so with that set, whilst we've got items in the collection, so if seek of that input is true, then we want to recur, so we're going to iterate through. We're going to pass in as the collection the rest of the input. So we just iterate through, take the rest of the collection and go on. And if the predicate on that first item of the collection is true, then we can conj into result, into our vector, the first item of the collection. So what we're going to do is, if the predicate is true, we will take that value and add it into our vector. And the way that conj works with vectors, it will add into the end. So as we iterate through, the last item goes to the end of the vector, so we'll end up with things in the right order. If the predicate on that item does not return true, then we don't want to put that into our results, so we just return our result as is. So the first time round we'll just return with the empty vector, and as we recurse through, we'll return as our result being the vector of all items that have successfully been filtered. So we'll recurse through until seek of the input, so the collection where we're at, is empty, and at which point we can just take that result, and in order to return it as a lazy-seq, we can just apply lazy-seq to that result. So there's quite a bit going there, but we're just iterating through our collection. Each item in turn, we're going to see if the predicate holds true. If it does, we're going to add that item into this vector. If not, we ignore it and carry on. At the end, when the collection is empty, we just convert that vector of the filtered items into a lazy sequence. And we can do this, and we can write a bunch of tests and they pass. So that's great. We have a test passing, but do the tests actually show us the laziness of the function, of the filter? And so we can see this by just running some examples again in the REPL. So here's an example where we're going to pass to our filter function just the function even. So this will return true for any even numbers. And we can pass in the range 10. So this is going to be collection of all the integers from 0 through 9. And so this returns the sequence 0 to 468. Okay, so that's great. And that result, so the result of applying passing even and the range 10 to my filter, we can take the first two items of it. So take 2 from that result, and we return the collection with 0 and 2 in. All good so far. What happens though if we just pass in range? So we mentioned before when we introduced filter and lazy sequences that they can be infinite. So range is infinite. It's going to be a range of integers from 0 all the way up through infinity. So we should be able to filter that range, that collection, filter using even again, so we should just get all of the even numbers, and take the first two. So it should be 0 and 2. The first two items that successfully pass the predicate of even with the range. But it doesn't. It never actually completes. Why is this? Not really because cats are not lazy, it's because conj is not lazy. So we use conj as we were building up the function. And conj is not lazy. And the reason it's not is that conj depends on the collection type. So depending on, with vector we were adding items into the ends of the vector. Other collection types work differently with conj. And so because of this, the result needs to be realized immediately. So with conj, depending on the collection type, the result is realized immediately. So what we were seeing there with our initial version of filter was that we were having to try to realize the result of applying the predicate even to each item in this infinite collection before we could do anything else. And of course, computing an infinite collection takes some time. So in order to get around this, we can use cons. We saw cons before, one of the sequence abstraction functions. So with cons, we're always going to be adding the item to the start of the collection. And because of this, we can evaluate lazily. So let's just rewrite our function where we're doing it lazily using cons. So this is what we can end up with. And what we're going to do is we're going to pass to lazy-seq. So we're going to create a lazy-seq from what we pass in, which is the when block. So when the collection has got items in, so when seq call is truthy, we're going to do something depending on whether the predicate holds true or not. So if the predicate on the first item of the collection is true, what we're going to do is cons, so we're going to add that first item of the collection into all of the other filtered collections to come. So all of the other filtered collections to come we get by recalling my filter with the predicate and just the rest of the collection. If that predicate didn't hold true, we just want to ignore that item in the collection and carry on with the rest. So we're always going to, we start from the beginning, we add that result into all of the other results to come. So in this way, we can now rerun this, reevaluate this, where we're taking the first two of the results of passing even and range to our filter function. So now, because we're just adding the items in from the beginning to the rest of the things to come, and it's done lazily, when we call take two, that's when we actually start evaluating the lazy sequence. So my filter, even range, gives us a lazy sequence. Nothing is actually evaluated until we call it. So when we do take two, we start evaluating it, and we only need to evaluate what we actually need. So in this case, the first two items. And so it returns the result nice and quickly. So now we've built a function that is lazy, and it gives us our model of filter. Just something that caught me out when I was first looking at Clojure, it's worth a note with these functions, is that you don't always return the same data structure as you started with. So, as an example, how do we get a vector containing just the even numbers given an input of a vector 0, 1, 2, 3, 4, 5? So when we pass even and that vector to our filter function, we return a lazy sequence. Now, a lazy sequence is not the same as a vector. So if we want to get back a vector in order to carry on processing, then we need to pass that result into a new vector. So we create that. So it's something to look out for. Okay, so with filter, let's quickly move on to map. Map is going to, again, return a lazy sequence. And this time, the lazy sequence is going to be the result of applying a function to the set of the first items of each of the collections. We can have any number of collections. And then we carry on with that until at least one of the collections is empty. Again, like with filter, you can have the case where we don't pass any collections in, and that would return a transducer, and we're not going to look at that in the model that we're talking about today. Okay, so let's start building this up. And we'll look first at the case where we just have a single collection. And we can write this up in an analogous way as we wrote up the filter function. So we define our map function. In this area, we're going to just have a filter and one collection. And we're going to have a when block in the same way as we did with filter, but we don't need the predicate this time. All we're going to do is we're going to add the result of applying the function to the first item in the collection to all of the rest of the mapped items to come. So in this way, we end up with the lazy sequence as we did with filter. So that works, and we can use the same sort of technique to do 2, 3, however many collections. So here's the example with 2 collections, new rarity, collection 1 and collection 2, and we just need to say when both collections have items in, so when C1 and C2 both return truthy when we apply seek to it, then we're going to apply the result of applying the function to the first item of C1 and the first item of C2. We're going to add that to all of the rest of the mapped items to come. So this works. We can do something similar moving forwards, but of course we can't have an infinite number of rarities. So what can we do to deal with the fact that we can have any number of collections? So this took a little bit of thinking about how we can build up lazily. I find actually just putting it into English, putting into words what we can do is a really useful approach before actually looking at the code. So in order to map across first items of all the collections, what we can do is take all of those input collections and put them in a single sequence. So we have a single sequence with all of the collections, and then reorder that sequence so that the first collection becomes all of the first elements, the second collection becomes all of the second elements, etc. So we're going to want some sort of a reorder function that's going to take our collections and then like turn them on the head, so all of the first items are together and all of the second items are together, etc. When we've got that, we can map the result of applying our function to each reordered collection in turn. So we'll do map with the first collection containing all of the first elements, and then with the second collection, etc., until we get through to the end. So how does this actually look? We can add the rarity where we have a function and more than one collection. So C1 and any number of collections to come. So first bit we need to do is create this single sequence. So we can do that at the end of the bottom line. We're going to cons C1, so the first collection, into all of the other collections. So we're going to end up with one sequence with all the collections. And we're going to pass that to our reorder function that we still need to write, and that will give us our reordered collection, so we've got all of the first items together, all the second items together, etc. When we've got that, we can apply the function across each of those in turn, mapping the result. So we can map with a function on that reordered collections. So we need to write our reorder. Oops. And we can do that by looking when every collection in our new sequence with all the collections, when everyone has got items in, because remember with the definition of map we just discard anything left after we've mapped through until one of the collections is empty. So when everyone has got items in, what we're going to do is we're going to map first function across the collection and add that to all of the reordered collections to come. So that's going to give us our reordered lot of collections, and to which we're then applying the function to. So you'll notice here that the two functions are calling each other. So they're mutually recursive. My map function is calling reorder, and reorder is calling my map. So in order to work with this, we just need to declare one of them up at the top. So we're going to declare my map in order for this, in order to deal with the mutual recursiveness that we've got. So in this way, whether we've got 1, 2, 3, or however many of collections, we're going to be able to reorder them and map through by first element and then second element, etc., in order to get our result. So in the last few minutes, we'll just look at the last of the functions we're going to look at, and that is pmap. So parallel map, exactly like map, except that the function is applied in parallel. It's semi-lazy. We'll look at what this means. When I first looked at it, it's like, yeah, I'm not quite sure what you're meaning by semi-lazy, but when you start working it through, it makes sense. And the bottom line is important. It's only useful for computationally intensive functions. There's no point using pmap when the processing is not intensive. Otherwise, the extra overhead deters from any benefits that we get. So let's build up a mimic of a computationally intense function. And we can do this by just applying a sleep. So here I've just defined a long-running job. We can take any number of arguments, and we're going to sleep the process for 1,000 milliseconds. And then just going to do something with those arguments. So in this case, I'm assuming that we're just going to get numbers coming through, so we're just going to apply addition. So we're going to add 10 to all of the arguments. So we can have different functions in here if we want to be more generic about what this long-running job can handle. So we've got a long-running job, and so we can write a text, just make sure that this works. So we can just bind the system time at the start to a variable st, and then run the long-running job. So the long-running job, if we just pass in one number, it's just going to sleep for the 1,000 milliseconds, do the computation, and so the total time should be just over the 1,000 milliseconds. So the 1,000 milliseconds sleep, and then whatever time it takes for the computation. So after we've done the long-running job, we can just get the time again, take that away from the start time, and then convert it through into seconds. And we can say that the time it takes to run this function should be more than 1 second. We've got the 1,000 millisecond sleep plus a small amount. And that test passed. So we get a long-running job function. So what about if we use map? So we can do the same here, but instead of just calling long-running job, we can pass to map the long-running job and a collection. So again, we can say that it should take more than a second. In fact, it should take more than 4 seconds to run this, because we're running one at a time. As we iterate through the collection, we're passing it to long-running job. It takes a second to sleep and then does the computation. But this test fails. And it fails because map is lazy. So we're not actually measuring the time to compute the result. We're just measuring the time to make a new lazy-seq, and that's not all that long. So in order to have this, in order to properly mimic a long-running job, we need to actually execute it. And so to do this, we need to realize that lazy sequence. We don't want to just make the lazy sequence, we need to realize it so it actually executes. So again, we can set the system time, and then we can pass the map with the function in the collection to some function that realizes the lazy-seq. And here I've just written one where we bind to res the result, applying map, whatever map it is, to the function in the argument. So we get our lazy-seq, and then we call it. So when res, so when we're calling our lazy-seq, and so evaluating it, and then we can iterate through that way, and thus realizing the lazy-seq, and so getting that test to pass. So running map with that long-running job actually does take the 4 seconds. So in order to write our pmap, we need to use parallel computation, and we can use Clojure futures for this. And so with futures, we can evaluate them in any available thread pool, and that result is just going to be cached until we call them with deref. So in this way we can utilize the multiple threads. So writing a test for this, when we have a successful pmap, it shouldn't take much more than 1 second in order to evaluate any collection if we're running them all in separate threads. So how can we do this? We could let results be the results of mapping the function across the collection as futures. So we're going to create futures of applying the function to each item in the collection. And then we can deref those results. So we're going to create our futures and then we can deref them. But this actually fails, and it still takes over 4 seconds. And the reason it is because pmap is semi-lazy. So what we need to do is actually generate all of the futures before we start to deref. If we generate them lazily and then deref, we're doing all of the work still at the same time. So we can do this by using the trick that caused us problems earlier with filter. And we can do that by using conj. So instead of being lazy as we're creating the futures, whilst we're going through, we can add each future, conj it into a collection. And so every time we go through, because it's conj, it gets realized, so we create the future. So in this way, we end up with a collection, a vector of our futures where the function has been applied to each item in turn in the collection. So now in this way, we're actually starting those futures so they can compute. And then we can call in the bottom line, when we've got them all going, we can deref them. So we can just map our futures and deref them into the actual results. And in this way, we actually work in parallel. And in the same way we've seen before, we're iterating through, as we were creating the futures, we were iterating through taking our collections and returning a single value, in this case, a vector. And so we can rewrite and reduce in a similar way as we've seen before. And then we can extend to multiple collections, again, in the same way that we did for map. And so we define our pmap nice and concisely using the futures in order to do the parallel computation. So I know I've been going for almost an hour now, and we've gone through a few of the Clojure functions, and we've written models, and we've learned a lot from it. I learned an awful lot going through this, so about what sequences and collections actually were, how recur actually works. We looked at futures and lazy sequences. And so whatever language you're doing, I think you can get an awful lot of value by really digging in, building models for the different functionality in the language, and getting understanding about how the guts work. And when we understand that, when we actually understand the fundamentals of what we're doing, we can have confidence in the code that we're doing. We can have confidence that it is going to do what we actually want. So I'm going to stop it there, open up for questions if you've got. If you're interested in learning more, it's been a bit of a whirlwind tour today. I'm going to be doing some training on the subject in September. So we can take a slower pace introduction into Clojure in the first day if you've not had much experience to date, and then do a dig deep into the guts of the language. And then in a third day, we'll look at how we can actually have more confidence that the code is doing what we want. So at this point, I'm just going to open up if anyone has got any questions. I think you can add them in through the questions tab in the control panel. Okay, so we've got a question through from Tracy Holmes. Why do first and rest not also produce sequences. So first is just taking the first item out from the collection, so we just return that actual item. Rest is going to return a sequence of the rest of the collection. So in that case we take everything but the first item. So hopefully that answers that question. Are there any other questions coming through? I've got a question for you then, just whilst we wait and see whether any more come through. That's how can we be confident that the code that we write is actually doing what we want? So in this case, and I touched on it as we were building things up, we were writing unit tests. And so that gives some confidence that things are working as we want. What I'd like to point you to, well, the question, how many tests should we actually write? And we can write more and more tests, give us more confidence, but every test has some overhead. It's code that we have to manage, and we'd never guarantee that we're going to hit all of the edge cases. So this type of work, where we're effectively comparing our result with something already out there, like if we're refactoring our code, we can just compare the result to what already exists and compare that they're correct rather than the actual answer. So in this case, probability-based testing can be useful. So that can be something that's worth looking into as well. Okay, so I'm not seeing any other questions, so I'd like to just thank you all for coming on the call today. I hope you found it interesting. If you'd like to reach out, if you have any questions, you can find me on Twitter, so @Graham_JP, and my blog is at jonathangraham.github.io. Okay, well, thank you all very much, and I look forward to hearing you all. Have a good day. Goodbye.